very complex. Okay, apparently there's one person in the room that doesn't make mistakes. But even the best programmers in the world, they sometimes make a mistake. And if you make a mistake, then it means that your program doesn't do what you want. And someone at some point has to go in and fix the problem. And in conventional languages, this is kind of, it can be very tedious, but it's also simple because you attach the debugger and you run your program in the debugger and you kind of trace the execution as it's going to see, okay, is it still correct? It's still correct. And then you hope to find a place where it no longer is correct. And then you can find some clues to fix the problem. But there's an issue with this, and that is that it only works if there's a correspondence between the source code, the structure of the source code, and the structure of the generated code that is ultimately running, so you can do your detective work. So, and that's sort of captured here. I've noticed that the source code, and there's this green part, the blue part, and the yellow part, and after we compile it with non-optimizing compiler, the structure it's now assembly code, so it's difficult for humans to read it, but the structure is still the same. The green part is still first, and then the blue part, and then the yellow part. But in a little bit more crazy languages, like the ones we are discussing today, like Accelerate or Stack, that do a lot of optimizations, this correspondence is just not there. The code that is ultimately generated looks completely different, unrecognizable from the source code that you give it. Functions are inline, data structures are completely rewritten, changed, fusion merges operations together, intermediate values, they disappear. You don't have all the intermediate steps. That becomes really difficult. And the structure, as you can see, is very different. The blue part is spread out, the green part is at the beginning and the start. There's now this purple part that wasn't even in the first part of the program. So where did that even come from? So this is a real challenge. How do we debug optimized code if it looks unrecognizable? And what you can do, of course, is not optimize, right? That's a simple solution. But that is really not an option, because especially these array languages, you need to optimize, because that's the point of using. If you don't optimize, the runtime can go from minutes to hours. So that's just not an option. Then you spend days trying to recreate the program. If you even can then detach debugger, because another reason why this correspondence doesn't exist is because high-level abstraction generates so much code to support the abstraction that is also really difficult to map back. So you cannot really go back in that situation. And what you can also do is you try to encode all this information into debug symbols, and you try to go really hard there, but that's a really complicated thing. And every step that the compiler takes in this process needs to be captured in the symbols. If one step is not really captured well, that sort of breaks the whole thing, and that takes a lot of time and takes priority away from other features. And that's why you can see in practice that it's not really done to its effect. So this talk is mainly about, in the context of a language called SAC, Single Assignment C, already mentioned Gabriele in the first talk. It's an array, pure functional first order array language. So it's also trying to do arrays, it's multidimensional arrays that you can do computations on. And it is a C-like code syntax, but it is really a functional language. So there is no pointers, and there's this conceptually, at least, there's not really a notion of memory. The arrays are always conceptually at least copied, but we use reference counting, and because of that, behind the scenes, the updates can happen in place if there's only one reference to array, but the programmer doesn't really know about that. But the important thing is that SAC is one of these languages that really takes the source code and mangles it a lot, and the final C code SAC goes towards to generate C code in the end really is unrecognizable from the code that you write when you program the code that the programmer wrote. It's unrecognizable from the code that is finally generated. So to show the rest of the talk, I want to have this one running example. It's a simple program that lends itself very well to the explanation of how we're going to tackle this problem, how the debug optimize code. And it's not like a serious program that you would write, but I hope you can imagine how this kind of stands in for a much more complicated program with a similar structure. So it's very important that everyone gets what this is doing. So I'm going to go through it step by step so everyone follows along. So first we start in main like we always do, and we ask the user for an integer. And then we take an integer and give it to iota. And iota is a function that generates an array of numbers in ascending numbers. So it goes from 0 up to n-1. So if you give n 5, you get an array of 0, 1, 2, 3, 4. And on 100, you get 0, 1, I'm not going to count to 100, but for 99, but you get the array of 99. Then we take this array, when you give it to foo 5 with a hard-coded value of 50, and that starts this chain of function calls. The foo calls foo 4, and foo 4 calls 3, 2, 1, foo, and then we end up at dangerous. And in this process, we do computations on the index. And then finally, in dangerous, we do a selection on the array. So that everyone, this is important because I will keep going for this program. So if anyone doesn't get it, then speak up now. And if you optimize this program, you can see that actually all this code that I just showed vanishes because there's this index here is known statically. So we can inline all these functions, and then we constant fold all the operations together. And then what we're left with is, oh yeah, I didn't say that. Of course, there's also a dangerous function here. So we also do another operation where we skip this chain of functions. We go directly to the attribute of that. But because the index is statically known, we can just skip all that. And we only are left with the two array indexes in the end. But n is not known because it only is known when we run the program, because it depends on the human. So all this code is gone. And now if you attach a debugger, right, all the intermediate steps are gone. You just only see 29,180. Good luck finding out where. So this of course, like, what is the problem with this program? That if you give an n that is too low, the array is too short, and then this is an out of bounds excess. If you give like 10, for instance, then this one will be fine, but this one is out of bounds. So that's the problem. If you give an n that is too low, then it doesn't, it's an out of bounds excess. But good luck finding out in which one of these it got high enough that it was out of bounds. You can't know anymore because the code is disappeared. And if you run this with no input, you indeed get this error message. And it's not really a nice error message. It's just like, okay, what's happening here? It's like, so you know there's an out of bounds selection somewhere deep down in the SEC sort of standard library. But you know, this is not really great. So what we can do is like there is something with a there's something with a selection here, and now it's time to say the problem with these debuggers is that you kind of need to keep all the states. So all the states of all the intermediate values need to be known for these debuggers to work well. And then you lose all the optimization to have all the intermediate values. But what is great about assertions, so what if you just tell the program which values you're interested in? And that you can do by adding assertions to the program, or type or predicates, predicates, the checks. And they are checks that you put in the code to say, okay, if this precondition holds, then you can call the function safely and everything is fine. And because, you know, we got in the error before, we got something with a selection, there's one function with a selection, so let's just put a precondition there. And SEC has this really nice syntax for that called type patterns made by Jordi from Nijmegen. Here we can express this precondition on the dangerous function. It's called a type pattern because we can kind of use the n from the type in conditions, which I personally think is one of the coolest things that Zach has to offer, because you can also even use this n in the body function. But that's a different story. So we added this precondition there, and then let's see what the code now generates if we optimize this program again. We can see it's the same thing, but now we have these two pre-checks that have been added, and this new function that we generated, and we assert if the n and the index are if the n index is less than 10 and if that holds, then it's fine. But of course, assert is a function that has a side effect because it can abort the program. And aborting the program is also a side effect. And for that reason, we need to also pass this uniqueness value, this unique value through the program. I mentioned that to sequence these side effects. This number, it looks like C, but it's still like a functional language. And we get this uniqueness value basically here, and then because we pass it there and we return a new value, we kind of have referential this transparency, because all these calls are unique calls. So you never have the thing that you call it a function with the same arguments and then some different behavior happens, because these values are unique, they're never repeated. This is a new copy. You kind of sequence the order of these checks. So this one can, by the compiler, can never be moved here because it needs the result of this function. And also notice that we return this as well. So these TFC, this TFC stands for the control flow. And because we return it, it means that it's a part, that these things are part of the result of the program, and that's why they cannot be removed. All right, so now we have this. We added the pre-check into the code. But still everything's gone, the rest of the code is all gone. But now we get much nicer error message. So we were right in the intuition, coming up with dangerous function, and now we're already much closer to where the problem lies. And that's much nicer. But the problem with this is, which call to dangerous was it? And of course, in this program, you can see that, right? It's probably this one. But you can imagine a larger program where it's not so clear which pre-check, which call to dangerous was the one that failed. So just to be clear, was it the one dangerous call at the bottom of the food chain there, or was it this one? And imagine if you have like 900 calls to function foo, function dangerous, you know which call is the one that crashed, that was had the error or had type violation. And to solve that, we would really like to know how we got to the point where the program failed. And what we want is actually a stack trace, right? We want to get a record of the function calls up to the point where something went wrong, and that is a stack trace, and that tells you which dangerous call it was. And this combination of type patterns or these assertions with the stack trace is a really powerful tool to debug your programs. But we cannot have, how can you make a stack trace? I mean, all the function calls have been removed, right? There is no stack in the memory to unwind. That doesn't exist. So if we cannot use a stack that is there in the memory, we just make our own stack. The virtual stack, a shadow stack that reflects the program as it was in the mental model of the program of the programmer right before the compiler starts to make all the changes to it. So early on in the compilation process, we have to add code to maintain this virtual stack.
Can I just a little bit? So if you said we have to add code, it's the compiler.
Yeah, so that's the compiler. Yeah, that's very clear.
Switch it on as debug mode.
Yes.
And the things.
Yeah, when I say we, I mean sort of the compiler. You're right. That's the compiler developer talking. So the compiler, the programmer does not write. The programmer doesn't even have to write these uniqueness types. They're also inserted automatically using something called their global objects. But I'll get to that. So how this works, we take each function call and we surround it with a push and a pop operation to keep the stack of function calls in our own virtual stack data structure. And important, and this also the key idea really is that these stack push and pop functions are injected in the same data flow as the checks, right? So then, this use the same unique value to sequence the push and the checks, and you can also have post conditions, but those I won't discuss. And the pop means that if the check fails, it can look at the current state of the stack based on these unique types, and then generate the stack trace. That is always basically correct as if you were running the unoptimized version of the program, but it's still all the code gone. So does everyone understand this? It's just the key.
You repeat again this concept of this unique so this TCF something special.
Yeah, it's basically you can imagine a variable that you can only use once. So if you, for instance, have a function foo, and then you have a, which is a unique variable, you cannot have a as two places in the pass arguments to foo. Right? Do you see that? So you can never use this value twice. Do you want to? Okay. Yeah. So and the idea with that is that this is also like.
So it's like a global variable. I can only refer to it once in the global context. So
no, because well, it is actually a global variable. That's more stack specific. The idea is this is actually TFC. This is a TFC 0, and this is a TFC 1, 2, 3, 4, 5. It actually makes a new one every time. That is unique. And this TFC, if you would have TFC 0 here, there, and there, then it would not be allowed. And because it's actually every time a unique variable, you can have functions with side effects without kind of breaking the referential transparency, because there is you don't really have a call with the same arguments that has a different effect. It's always the same, yeah. Okay. Yeah, and so this is not a trivial thing, right? Because we actually first inject these push and these period posting, and then later on we add these uniqueness types, are sort of automatically added because we sort of specify that these functions have an effect on this unique variable. So that's more details, and you can read about it in the paper. The point is that that's not a trivial thing, but that was already present in stack, and because we had already adding these push and pulls, it was actually not so large of a thing to add. So if you have these uniqueness types and they work well, adding this is just relatively little amount of. All right, so if we now take this transformation and apply it to a program, we get this, right? So the call is still there, we like unit, iota, so there, but we add these push and pop operations around all the function calls. And so especially here, you can see that all the push calls are pushed first, then we do the dangerous check, we actually do the computation, and then we pop everything again. And then we push the other dangerous, and then we do the second index and return the results. And again, because of these uniques, because they're all like different unique values, the compiler can never rearrange the order of these things, which also means that if you do it at the start of the program, it's kind of separate from the rest of the code, because the rest of the code can still be optimized. You keep optimizing it, but this will always stay. So it's like a sort of second computations that run set next to the actual computation of your program, which also means that if you have this, you kind of add optimizations to your compiler without having to change the system, which if a debug symbols you do need to then again encode that transformation. That's not needed. Okay. So now we get this beautiful error where we get the same error we got before and a nice stack trace from main all the way to the full dangerous call that that's not there. And with this in hand, it's much easier to find where the mistake is if we know which decimal is about to put. This is already really great, but we can do even better because why only push the name of the function, right? We can push much more information. Once we have this infrastructure, we can push all kinds of interesting information. Like, for instance, the file name, the lines of the location, like where is this located, so we can generate nice error message. But more interestingly, the edge of the function, which then allows us to push the dimensionality and the shapes of the arguments. Because in theory, you can say, okay, right, why don't just push the values of the arguments of functions into the stack? But that kind of defeats the optimizations again, because then you need to have all the intermediate values. And so that doesn't really, that kind of breaks the point of optimizations. But only pushing the shapes and the dimensionality of the arguments, that is a really nice middle ground, because these shapes are very often statically known. So the compiler can usually figure out what the array, the dimensionality and shape of array is, and it doesn't mean that it forces array to be computed to be actually present at runtime. So in this case, in this example, array is still present, but in many cases, almost always actually, the compiler just statically knows these shapes. And just know that dot is the same as C, that it's a periodic function that you can push as many of these pairs of dimensionality and shapes into the push as you want based on the error. So we can push much more information, and if we do that, we get this program that same as before, but we just push more information. As you can see, the shape and the dimensionality at the end here is all statically known. So we don't actually we're not really relating this shape of the code that does the checks and the push and pulls to the rest of the program here. But you can imagine that sometimes it would be necessary to do some extra to intermingle the actual code and the shape computation in the stack trace, and then we would create some events. And then you get this nice stack trace. So this stack trace actually has every step the shape information of the arguments here. So this shows that the array has 1,000 items. So that means that we gave the input, we gave n 1,000 when we ran it. And the shape of a scalar is just an empty array. And we also have the locations now in the stack trace, right, in the line and file location, which is also generally a difficult thing. If you map back from generated with code, it's difficult to find it. That is already a quite difficult problem. Like, how do you find the location of how you map back the location of generated code into the source code? There it is. Now we can do one nice thing that sort of the functional nature of stack allows us to do is we can notice that if you take the push for read int and the pop, there is actually no check in between these two operations, which actually allows us to just take them out, because we know for certain that there will never be a runtime error in this part of the checking process. More formally said, if the unique value consumed by a pop has been created by a push, we can actually remove the push and pop pair because there's no check in between. And we know that because of these uniqueness types, we can really, because they're sort of linked in the AST, we can jump from here, we can kind of trace back the order of these things, and we can really kind of easily remove many of these push and pulls for paths where there are no checks. So it's just gone. And then things like this. Just to show that it's gone. So again, if we move the type pattern from the dangerous function into O3, we no longer actually need to push this bottom we no longer need to push this and dangerous onto the stack because there's no checks there. You can see that here. Right now we only have to push 2, 5, 4, and 3, then to the check, and then we can pop again because there's no check on dangerous, so dangerous doesn't need to be checked. And this is really nice. Through how the automation works, you repeat this all the time, right? So if you remove one pop and push, because this unique value is produced by a pops, it's not produced by a pop, so you cannot remove it. But then if you, let's say, if you go, sorry, if you go, yeah, it's a bad example. But if you remove one pair, then you can usually remove the next pair and sort of keep going. And it's really satisfying how you can remove the entire chain of pops. And this optimization, really, I can see I got a short text base here. And this optimization really makes it so that the overhead of this stack trace is very low. And the interesting thing here is that his running the optimized version with the stack trace and the checks enabled still faster than running the non-optimized version. That is the key point. And without these optimizations of actually removing the unused pushes and pops, or the ones that don't have checks in between, this is not always the case. Actually, it can be that the program still runs that the non-optimized version actually faster, but that also kind of depends on how well the implementation of this push and pop are optimized, of course. But if you remove many of them, then you can see that very clearly here. If you run the optimized version with only the stack trace, so then you would not add any check, you only add the push and pops. The runtime is basically the same. These are like measurements, the standard deviation errors. This is basically the same, but all the push and pops get removed again. So these are kind of the same programs. And even if you run the optimized version with the checks and the stack, it's still way faster than running the non-optimized version, especially with this quick hold. The non-optimized version, we had to stop it after 1 hour. It just didn't. It was just non-feasible to run that one. But the optimized version with the checks and the stack, we could run, and we easily debug it. We had all this information. Now I want to zoom out a little bit, and if you have a program that has a mistake, what you usually have is some point in the call graph where you make the mistake, and later on you create this mistake sort of propagates to the program, and then suddenly you notice that the program doesn't do what you want. There's a failure. And the vision of this approach is that you kind of add all the domain constraints to all the functions, and then what you get is that you get the stack, you move the failure to the fault, and your program stops at the outer problem boundary. So it stops right when the mistake happens. And you close this gap, the fault failure gap, between the place where you make a mistake and the failure. So that is what we want to do. And then to add all these domain constraints. But of course, they have to be correct, which we have no real way of checking. And if you don't know, like some constraints might be very costly. Like most of the time, we add like some simple shape constraints that gets you a lot. But I could also imagine constraints where you need to check if an array is sorted, for instance, and or maybe if a matrix is invertible, and that is of course much more expensive. All right, so what I presented here is a really different approach from normal debugging, right? Normally you try to encode all this information into a kind of a separate location, into either the debug symbols, or you're trying to do this mapping back. But here we try to encode all this information in the program itself, which then very nicely just maps it to the hardware itself, but we can still maintain all this nice information. And it's a much more simple approach as well. You can get a nice stack trace without even having the functions runtime to debug. And what is also nice is that the programmers can kind of decide themselves how much information they want to store in these stack traces. The shapes are optional, you don't have to do that. So then you can save some performance if you don't need the shapes yet, because they might cause some interaction with the rest of the computation. But because that is optional, you can kind of tune that yourself. And really, the nicest part as well is that this functional nature of SEC allows us to do this great optimization that we can remove the consecutive pushes and pops. to get this without very low overhead, and I think this is a really excellent way to find faults in your program, even if you. All right, thank you for listening.